Rutherford's students and their successors became pioneers in this new atomic age. They discovered isotopes, atoms of the same element with different numbers of neutrons, explaining why some forms of an element were stable while others were radioactive. They also identified that when a nucleus split apart or fused with another, vast energy was released. This discovery would soon change the course of human history. In 1938, Otto Hahn and Fritz Strassmann in Germany conducted experiments bombarding uranium with neutrons. To their astonishment, they found that the uranium nucleus sometimes broke into two smaller nuclei, a process later called nuclear fission. Lise Meitner and Otto Frisch provided the theoretical explanation. The neutron had triggered the nucleus to split, releasing energy according to Einstein's famous equation. For the first time, humanity had uncovered the mechanism of atomic energy. Inside the nucleus lay a force so potent that, when unleashed, it could power stars or destroy cities. The discovery of fission marked the moment when the study of the atom's structure became inseparable from the destiny of civilization. As the world descended into global conflict, this newfound understanding was harnessed with terrifying speed. The Manhattan Project brought together the greatest minds of physics, including Niels Bohr, Enrico Fermi, and Robert Oppenheimer, to build a weapon based on the splitting of the atom. In 1945, when the atomic bombs were dropped on Hiroshima and Nagasaki, the hidden power of the atom was revealed to the world in fire and shadow. The same knowledge that had begun as a quest for understanding had unleashed the most destructive force ever created by human hands. Yet even amid the horror, the discovery underscored a deeper truth. The atom's internal structure was not merely a scientific curiosity. It was the key to creation and annihilation, to energy and existence itself. After the war, atomic research took a new direction. Scientists sought to use nuclear energy for peaceful purposes, to generate electricity, to power ships, to probe the mysteries of medicine and biology. Nuclear reactors, built on the principle of controlled fission, became symbols of both progress and caution. The structure of the atom had given humanity power over the building blocks of nature, but it had also revealed the ethical weight of that knowledge. Meanwhile, the scientific quest pressed on. If protons and neutrons formed the nucleus, what were they made of? Were they fundamental, or did they too have internal structure? The mid-20th century brought a flood of discoveries that would revolutionize physics once again. In the 1950s and 1960s, particle accelerators revealed a bewildering zoo of new particles, pions, muons, kaons, and dozens of others. The elegant simplicity of the atom seemed lost in a sea of complexity. Physicists were faced with a daunting question: could all these particles be made of even smaller components? The answer began to emerge in the 1970s with the development of the quark model. Physicists Murray Gell-Mann and George Zweig proposed that protons and neutrons were not fundamental after all, but composed of smaller entities called quarks. Each proton contained 3 quarks, bound together by the exchange of particles known as gluons. The strong nuclear force, which held the nucleus together, was now understood as the result of quarks interacting through these gluons. This new framework, known as quantum chromodynamics, completed another layer in the hierarchy of matter. The atom's internal structure was far richer than anyone had imagined. A complex interplay of quarks, gluons, and leptons, governed by the rules of quantum mechanics. In this quantum world, reality behaved in ways that defied classical intuition. Quarks could never exist alone. They were confined within protons and neutrons, eternally bound by the color force of gluons. Particles could pop into and out of existence in fleeting bursts of energy. Space itself seemed to shimmer with virtual particles, a restless vacuum that was anything but empty. To map this hidden universe, scientists built ever larger particle colliders, machines like the synchrotron, the tevatron, and eventually the Large Hadron Collider in Geneva. Each experiment brought humanity closer to understanding the fabric of matter and the forces that shaped it. The standard model of particle physics emerged as the grand synthesis of these discoveries. It described all known subatomic particles and the forces that govern them, electromagnetic, weak, and strong, in a single mathematical framework. Yet even this masterpiece was not the final word. It left gravity unexplained and hinted at deeper layers still unseen. Through all these advances, one thing remained clear. The atom was not a static entity, but a dynamic, vibrating field of energy and interaction. The nucleus pulsed with quantum forces, the electrons danced in probabilistic clouds, and the boundaries between particles and waves dissolved into pure mathematics. The deeper scientists looked into the atom's structure, the more they realized that simplicity was an illusion. What appeared solid and stable was, in truth, a storm of motion and transformation. Every atom in the universe was a tiny theater of creation, particles colliding, merging, and decaying in an eternal cosmic dance. Yet amid this complexity, patterns emerged. The same principles that governed the atom also shaped the cosmos. The fusion of hydrogen nuclei in the hearts of stars, releasing light and warmth across the void, was the same process that had first forged the elements. Every carbon, oxygen, and iron atom in our bodies was born in those ancient stellar furnaces. The study of the atom's internal structure had thus revealed something extraordinary: the unity of matter, from the smallest particles to the largest galaxies. This revelation transformed not only science, but philosophy. The boundaries between the microscopic and the cosmic blurred. The atom was no longer a symbol of isolation, but of connection. A microcosm reflecting the same principles that governed the universe at large. As the 20th century drew to a close, the tools of atomic exploration grew ever more sophisticated. Scientists learned to manipulate single atoms with precision, using scanning tunneling microscopes to move them one by one. Quantum mechanics, once an abstract theory, became the foundation of modern technology, from semiconductors and lasers to quantum computers. The atom, once a mystery of philosophy, had become the cornerstone of modern civilization. Yet its inner structure still held unanswered questions. What lies beyond the quarks and leptons? Are there hidden dimensions, unseen particles, or deeper symmetries waiting to be discovered? The search continues, driven by the same curiosity that began centuries ago with a question as simple as it was profound: what is everything made of? Each new discovery adds another layer to the story of the atom, but the deeper we go, the more mysterious the picture becomes. The boundaries between matter, energy, and space blur until they seem to dissolve altogether. Some physicists now suggest that particles themselves may be manifestations of vibrating strings of energy, an idea that, if proven, could rewrite our understanding of existence once again. In the grand sweep of history, the discovery of the atom's internal structure marks one of humanity's greatest triumphs. It represents the moment we learned that reality is not what it seems, that the tangible world is woven from the invisible threads of energy and force. From the first spark of curiosity to the colossal machines of modern physics, this journey has revealed both the beauty and the fragility of the universe. The atom's discovery was not merely scientific. It was spiritual in its implications. It showed that the universe is unified at every level, that creation is an ongoing process, and that the same energy that burns in the stars courses through our own existence. The deeper we look, the more we realize that understanding the atom is, in a sense, understanding ourselves. We are made of stardust, the ashes of ancient atoms born in distant suns, recycled through time into planets, oceans, and living beings. The internal structure of the atom is not just a fact of physics. It is the story of life itself. As the 21st century unfolds, scientists continue to explore the atom's inner realms with ever greater precision. Particle colliders probe the quantum frontier, space telescopes trace the cosmic echoes of atomic processes, and quantum computers harness the atom's strange behavior to perform feats once thought impossible. Yet for all our progress, the journey is far from over. The more we uncover, the more questions arise. Perhaps that is the true legacy of the atom's discovery, that knowledge is endless and wonder eternal. Each atom, silent and invisible, carries within it the memory of creation and the promise of discovery. From the first spark of curiosity to the glowing screens of modern laboratories, the quest to understand the atom's internal structure has reshaped not just science, but the very way humanity sees the universe. What began as a search for the smallest piece of matter became a revelation of infinite complexity. Within the atom lies the story of energy, transformation, and interconnectedness, the story of the cosmos itself. In the end, the atom is not merely a particle of matter. It is a symbol of human curiosity, a reminder that beneath the familiar lies the infinite. And as we continue to explore the depths of its structure, we are, in truth, exploring the boundaries of imagination, reaching toward the moment when the smallest and the greatest, the visible and the unseen, finally meet in one eternal unity. The revolution in atomic science did not end with the discovery of the atom's internal structure. That was only the beginning, a prelude to a deeper understanding that would challenge not just the limits of matter, but the boundaries of human thought itself. As the 20th century unfolded, the classical world of certainty gave way to a universe of probabilities, paradoxes, and unseen realities. This was the rise of quantum theory, a scientific and philosophical transformation that forever changed our perception of nature. In the early years of the century, scientists faced a puzzle that defied all previous logic. The atom, as described by Rutherford and Bohr, seemed stable only if electrons occupied certain energy levels. But why? Classical physics could not explain this mystery. The equations that had once governed planets and pendulums failed completely when applied to the tiny, restless electrons moving inside atoms. Something deeper was at work, an unseen order behind the chaos. It began with Max Planck in 1900, who discovered that energy was not continuous, but came in tiny packets called quanta. This simple yet radical idea suggested that the universe was built not from smooth waves of energy, but from discrete bursts, the building blocks of light and motion. Soon after, Albert Einstein expanded this vision, proposing that light itself could behave both as a wave and as a particle, a photon. With that, the first cracks appeared in the walls of classical certainty. Then came a new generation of thinkers who dared to reimagine the invisible. Louis de Broglie proposed that if light could act as a particle, perhaps matter could act as a wave. Erwin Schrödinger built on this insight, describing electrons not as tiny orbs spinning around the nucleus, but as waves of probability spread through space, a cloud of potential existence. Werner Heisenberg went further, showing that one could never know both the position and the momentum of a particle at the same time. This uncertainty was not a flaw in measurement, it was a fundamental property of reality. The atomic world, once thought mechanical and predictable, was revealed as a realm of mystery and paradox. In this strange landscape, particles could exist in multiple states at once, connected across vast distances in ways that defied logic. The universe seemed to whisper that certainty was an illusion, that beneath the surface of matter, nature danced to a rhythm that could only be described by probability and possibility. Niels Bohr, one of the great architects of atomic theory, embraced this uncertainty. He introduced the concept of complementarity, the idea that contradictory aspects of nature, such as wave and particle, were not mutually exclusive, but both necessary to describe reality. The world, Bohr argued, could not be captured by human intuition alone. It had to be understood in terms of what could be measured and observed. The atom had become not just an object of study, but a mirror reflecting the limits of human knowledge. Quantum theory did more than explain atomic behavior. It reshaped the foundations of science itself. It forced physicists to accept that observation could change the outcome of an experiment, that reality was not fully determined until it was measured. This was a staggering idea. The act of looking could shape what was seen. The observer and the observed were intertwined in a cosmic feedback loop, where consciousness and matter seemed to meet at the edges of understanding. As the decades passed, the implications of quantum theory spread far beyond physics. It became the foundation of modern technology, from transistors and lasers to computers and medical imaging. Every smartphone, every satellite, every digital signal carries within it the legacy of quantum discovery. What began as an abstract theory of subatomic motion became the engine of modern civilization. Yet even with its success, quantum theory remains profoundly mysterious. Its equations predict outcomes with astonishing accuracy, yet they describe a world that defies common sense. How can a particle be in two places at once? How can one particle instantly affect another across light, years of space? The deeper scientists probe, the stranger the answers become. But perhaps that is the true beauty of atomic science, that it teaches us humility before nature's complexity. The quantum revolution did not give humanity complete control over the universe. It revealed that the universe is infinitely deeper, subtler, and more interconnected than we ever imagined. Each discovery, each experiment, is a step further into the unknown, where mystery and meaning coexist. In the end, the revolution of atomic science was not just a change in theory, it was a change in perception. It showed that reality is layered, that certainty is rare, and that truth often hides in paradox. The atom, once imagined as a solid sphere, became a symbol of infinite potential, a bridge between matter and mind, between the known and the unknowable. And as we continue to explore this invisible world, we carry with us the same wonder that first drove humanity to look beyond the visible, the timeless desire to understand not only what the universe is made of, but what it means to exist within it. By the middle of the 20th century, the study of the atom had already transformed human understanding of matter and energy. Yet another revolution was waiting to unfold, one that would take the knowledge of atomic science beyond theory and into the realm of technology, changing not only laboratories but the very fabric of everyday life. The exploration of atomic energy, born from the same discoveries that had once seemed purely abstract, became the driving force of a new era. This was the age when the atom moved from the chalkboard to the real world, shaping both hope and fear in equal measure. The story began in the shadow of war, When scientists realized that the nucleus contained unimaginable amounts of energy, they also realized that this energy could be released in two ways: by splitting atoms apart through fission, or by merging them through fusion. Fission, discovered by Otto Hahn and Lise Meitner in 1938, became the foundation of the atomic bomb. During World War II, under the secrecy of the Manhattan Project, the world's greatest physicists gathered to harness this power. They built the first controlled chain reactions, demonstrating that a single gram of uranium could release energy equal to tons of dynamite. The consequences of this discovery were made real in 1945, when atomic explosions over Hiroshima and Nagasaki ended the war and opened a new, uneasy chapter in human history. The same principle that had created devastation also promised a new source of progress. Scientists and governments around the world turned their attention to peaceful applications of atomic energy. Nuclear reactors were built, not for weapons, but for generating electricity. In these reactors, controlled fission reactions produced heat, which was converted into power for cities and industries. The dream of an energy-rich future, one that could power civilizations without burning a single drop of fossil fuel, seemed within reach. Atoms for peace, declared President Eisenhower in 1953, capturing the world's fragile optimism. Across the globe, nuclear science became a symbol of modernity. From the United States to the Soviet Union, from France to Japan, reactors rose like monuments to human ingenuity. Atomic-powered submarines explored the deep oceans. Satellites and space probes relied on nuclear batteries to journey into the dark. Hospitals began using radioactive isotopes to diagnose and treat disease, while researchers applied nuclear techniques to agriculture, geology, and archaeology. The atom, once a symbol of destruction, was being recast as the engine of human advancement. Yet the promise of atomic energy came with a heavy burden. Accidents such as those at 3 Mile Island in 1979, Chernobyl in 1986, and Fukushima in 2011 reminded the world that the power inside the nucleus was not easily contained. Invisible radiation, silent and deadly, could turn progress into catastrophe. The same knowledge that illuminated cities could, through error or neglect, poison the earth for centuries. The dual nature of atomic power, creation and destruction, progress and peril, became one of the defining paradoxes of the modern age. Even as fission power shaped the 20th century, scientists looked toward an even greater dream: fusion, the process that powers the stars. Unlike fission, which splits heavy atoms, fusion combines light ones, such as hydrogen, releasing far more energy with far less waste. To create fusion on Earth, however, required recreating the conditions of the Sun, temperatures of millions of degrees and immense pressures. For decades, scientists struggled to control this celestial fire, building vast machines like tokamaks and laser-driven reactors. Each experiment brought humanity closer to what many called the Holy Grail of energy, a clean, limitless power source that could sustain the world for millennia. While fusion remained a challenge, its pursuit represented the enduring human spirit, the same drive that had led Democritus to imagine atoms, Dalton to describe them, and Rutherford to split them. The exploration of atomic energy was more than a scientific endeavor. It was a moral and philosophical journey. It forced humanity to confront questions about responsibility, ethics, and survival. Could we wield the atom's power without being consumed by it? Could knowledge be separated from its consequences? The atomic age changed not only science but culture. Artists painted visions of glowing cities and atomic landscapes. writers and filmmakers turned the atom into a symbol of both wonder and fear, a reminder of humanity's brilliance and fragility. The image of the mushroom cloud became the most haunting emblem of the century, a shadow cast by discovery itself. And yet, beneath that shadow, progress continued. Nuclear medicine saved lives, nuclear physics deepened our understanding of the universe, and nuclear energy remained one of the few technologies capable of producing vast amounts of power without emitting greenhouse gases. Today, as the world faces climate change and dwindling resources, atomic energy is once again being re-examined, not as a weapon, but as a potential savior. Advanced reactor designs, safer and more efficient, promise to deliver clean energy while minimizing risk. Fusion experiments have achieved record-breaking results, inching closer to the moment when science will finally replicate the power of the stars. The same curiosity that first revealed the atom's secrets now drives us toward using those secrets to sustain life itself. In the grand arc of history, the exploration of atomic energy reflects humanity's dual nature, capable of both destruction and creation, fear and hope. The atom gave us the power to end civilizations, but also the means to preserve them. It stands as a reminder that knowledge is never neutral. It is shaped by the choices we make. The revolution of atomic science was not just the discovery of how matter works. It was the revelation of what humanity is capable of becoming. In the glow of a reactor's core, in the silence of a medical imaging chamber, in the invisible pulse of fusion experiments, one truth continues to echo. The atom holds the energy of the universe, but it is human wisdom that must decide how that energy is used. As the 20th century advanced and the atom's secrets were unveiled one by one, humanity began to see its own reflection in those discoveries. The fifth great chapter in the revolution of atomic science was not only about the atom itself, but about the world that emerged from it, a world where knowledge of the invisible transformed every corner of human life. This was the rise of the atomic and quantum age, an era where scientific understanding spilled beyond laboratories, shaping technology, philosophy, and the way people perceived existence itself. By the mid-1900s, the foundations of atomic and quantum theory had already rewritten the rules of physics. But the implications of those ideas were just beginning to unfold. What had started as an abstract exploration of subatomic particles began to manifest in the inventions and systems that defined modern civilization. The understanding that matter and energy were interchangeable, that electrons could move through materials in predictable yet strange ways, gave birth to the technologies that now underpin the modern world: semiconductors, transistors, lasers, and the digital revolution itself. The transistor, invented in 1947, was a direct child of atomic science. It arose from the realization that electrons could be manipulated through the precise structure of materials, a practical application of quantum behavior. From that single discovery came computers, satellites, and global communication networks. Every smartphone, every digital signal, every byte of data in the modern world traces its lineage back to the study of atoms and their electrons. In this way, the atom, once invisible, became the foundation of a visible, interconnected civilization. Meanwhile, quantum mechanics continued to challenge the human imagination. It revealed that the universe was not built on fixed laws, but on probabilities, that particles could exist in multiple states at once, that their behavior could only be described in terms of likelihood rather than certainty. This uncertainty, which once seemed a limitation, turned out to be the source of incredible technological power. Quantum tunneling allowed engineers to design microchips smaller than the width of a human hair. Quantum optics led to the creation of lasers, used everywhere from medicine to communication. The strange behavior of subatomic particles had become not a philosophical puzzle, but a practical tool. As the understanding of atomic science deepened, so too did humanity's capacity to explore the universe. Nuclear power propelled spacecraft through the void, while atomic clocks, measuring time with unimaginable precision, became the heartbeat of global navigation systems. Even in the farthest reaches of space exploration, the atom guided humanity's path. The same principles that governed the nucleus of hydrogen powered the stars that scientists now studied. The microcosm and the macrocosm had become one continuous story. Yet beyond technology, atomic science reshaped philosophy and culture. It forced thinkers to reconsider the nature of reality, of knowledge, and of existence. If observation could change the outcome of an experiment, then the line between subject and object, between the observer and the world, was not as firm as once believed. Reality itself seemed participatory, alive, and deeply interconnected. The deterministic universe of Newton gave way to a dynamic cosmos of probabilities, a universe where certainty dissolved into complexity and where understanding meant embracing paradox. In art and literature, the atomic age inspired new forms of expression. Writers explored the moral dilemmas of nuclear power and the fragility of human civilization. Artists depicted atoms as glowing symbols of modernity and menace. The mushroom cloud, a shape both beautiful and terrifying, became a cultural icon, a reminder that the same science capable of building could also destroy. The human story had become entangled with the story of the atom, and the boundaries between scientific discovery and moral reflection grew ever thinner. As the century drew to its close, science entered an age of synthesis. Physicists sought to unify the forces of nature, gravity, electromagnetism, and the nuclear forces into a single, elegant theory. The search for this theory of everything became the new frontier of atomic exploration. Particle colliders delved deeper into the heart of matter, discovering fleeting particles that existed for less than a billionth of a second, each one a whisper from the universe's birth. These experiments did more than test equations. They traced the origins of creation itself. In the 21st century, the revolution of atomic science continues to evolve into the era of quantum technology. Scientists now manipulate single atoms to create quantum computers, machines that exploit the strange superposition of quantum states to perform calculations impossible for classical systems. In laboratories around the world, researchers trap atoms with beams of light, entangle particles across vast distances, and build devices that redefine what technology can achieve. The mysteries that once haunted the pioneers of atomic theory have become the tools of a new technological civilization. Yet beneath all the progress, one truth remains. Atomic science is a mirror of humanity itself, brilliant, curious, and forever walking the line between creation and destruction. It shows that knowledge is never neutral, that understanding carries responsibility, and that the smallest things can hold the greatest power. From the discovery of the electron to the decoding of the quantum world, from the energy of the nucleus to the birth of the digital age, the atom has guided humanity toward both awe and awareness. The revolution of atomic science was never just about the atom. It was about the awakening of the human mind. It taught that reality is layered, that everything is connected, and that the universe is far more mysterious than our senses can perceive. Each discovery revealed not only new facts about the physical world, but new ways of thinking about existence itself. The atom, in its infinite subtlety, continues to whisper the same eternal truth, that within the smallest particles lies the vastness of the cosmos, and within the quest to understand them lies the essence of what it means to be human. By the dawn of the 21st century, atomic science had already rewritten the narrative of human knowledge. The exploration that began with the curiosity of a few visionary minds had become a global quest to understand the universe at its most fundamental level. The sixth great chapter in this unfolding story is the era of the quantum frontier, the age when scientists began to merge the discoveries of atomic physics with cutting-edge technology, unlocking new powers and possibilities that once seemed like the dreams of science fiction. It is the story of how humanity, after centuries of peering into the atom, has learned not just to observe it, but to command its behavior, and in doing so, to reshape the future. In the laboratories of today, the boundaries between science and imagination blur. Researchers no longer simply study atoms. They manipulate them one by one, arranging them into patterns, trapping them in beams of light, and using their quantum properties to perform calculations that defy traditional logic. This is the world of quantum computing, a direct descendant of the atomic revolution. Unlike classical computers that store information as ones or zeros, quantum computers use qubits, particles like electrons or photons that can exist in multiple states simultaneously. Through the strange phenomenon of superposition, a single qubit can represent many possibilities at once, allowing computations to unfold in parallel across countless quantum realities. Entanglement, another astonishing property revealed by quantum theory, allows particles to remain mysteriously connected even when separated by vast distances. A change in one instantly affects the other, as if space itself cannot break their bond. Einstein once called this spooky action at a distance. But today, it forms the backbone of emerging technologies like quantum communication and encryption. These systems promise unbreakable security, transmitting information through the very fabric of quantum mechanics, where any attempt to intercept or measure the message would instantly reveal itself. The power of quantum control extends far beyond computing and communication. Scientists now use ultra-cold atoms, cooled to temperatures near absolute zero, to build atomic clocks so precise that they could measure the age of the universe to within a second. These clocks form the foundation of global positioning systems, financial networks, and astronomical observation. Every second of modern life, every transaction, every signal, every measurement is synchronized through the heartbeat of atoms. Meanwhile, quantum simulation allows researchers to model the complex behaviors of molecules and materials that classical physics cannot describe. By recreating the conditions of chemistry and biology at the atomic scale, scientists can design new drugs, develop superconductors, and explore exotic states of matter that may one day revolutionize energy storage and transport. The same principles that once revealed the structure of the atom are now being used to rebuild the structure of technology itself. In this new frontier, the atom has become not just an object of curiosity, but a tool of creation. The dream of harnessing atomic precision, building devices atom by atom, molecule by molecule, is giving rise to nanotechnology, where materials are engineered from the ground up. At this scale, the familiar rules of the macroscopic world give way to quantum behavior. Surfaces become sticky, electrons tunnel through barriers, and light can be bent and confined in ways that seem to defy nature. Humanity has entered a stage where the building blocks of matter are no longer just observed, but crafted into new forms of existence. Yet, as before, this power carries responsibility. The ability to manipulate the quantum world brings ethical and existential questions. What happens when computing surpasses human understanding? When quantum systems can simulate entire realities? Or when artificial intelligence merges with quantum precision? The revolution of atomic science, once confined to laboratories and textbooks, now reaches into the fabric of society, challenging the very idea of what it means to know, to create, and to control. At the same time, atomic and quantum science continue to expand our cosmic perspective. Through powerful telescopes and particle colliders, scientists trace the evolution of matter from the Big Bang to the present. The same quantum fields that govern atoms are believed to have shaped the earliest moments of the universe, rippling through space, time to form galaxies, stars, and planets. The discoveries made in the smallest scales echo across the largest, revealing a profound symmetry in the structure of reality. The quantum frontier is not merely a scientific phase. It is a philosophical awakening. It suggests that the universe is not a clockwork machine, but a living web of probabilities, connected by invisible patterns of energy and information. The atom, once thought to be the end of divisibility, is now seen as a doorway, a threshold into a deeper layer of existence where matter and mind, chance and causality intertwine. In this unfolding era, humanity stands at the intersection of the known and the unknown, armed with knowledge that can illuminate or devastate, empower or enslave. The atom, once the smallest of things, has become the grandest metaphor for possibility. Each new discovery brings both wonder and warning, reminding us that the ultimate challenge of science is not just to understand the universe, but to understand ourselves within it. As the quantum age advances, one truth grows ever clearer. The journey that began with the splitting of the atom has not ended. It continues in every qubit, every photon, every experiment that pushes against the edge of reality. The revolution of atomic science has evolved into the revolution of consciousness, a moment in history when humanity, for the first time, can look at the fundamental workings of the universe and whisper, not with arrogance but with awe, "We are part of this mystery." The story of atomic science has always been one of discovery, transformation, and reflection. Yet its final and perhaps most profound chapter is not about what has been uncovered, but about what is still unfolding. The continuing evolution of atomic research represents humanity's endless pursuit of understanding, a journey that stretches from the smallest quantum particle to the vastness of the cosmos. Even now, after more than a century of breakthroughs, the atom remains a mystery that refuses to be fully unraveled. What began as a search for the building blocks of matter has become a quest to comprehend the fundamental nature of reality itself. In today's world, atomic science is not a closed field but a living, breathing frontier. Every year, scientists delve deeper into realms that once seemed unreachable. The tools of this exploration, particle accelerators, quantum sensors, and powerful supercomputers, have become the modern telescopes through which we peer into the unseen. In massive underground laboratories, beams of protons race around circular tunnels at nearly the speed of light, colliding with unimaginable force. These collisions briefly recreate the conditions of the early universe, allowing scientists to glimpse particles that flicker into existence for less than a trillionth of a second before vanishing. Again, each of these fleeting events is a clue, a whisper from the origins of time, energy, and matter. The discoveries made in these experiments have revealed a universe more complex and interconnected than anyone could have imagined. Particles once thought to be fundamental are now known to be composed of even smaller entities, governed by intricate symmetries and hidden dimensions. The search for the elusive Higgs boson, confirmed in 2012, proved that the invisible fields pervading the universe give mass to matter itself. Yet even that monumental finding was only the beginning. Scientists now chase deeper questions. What lies beyond the standard model of physics? What dark matter makes up most of the cosmos? Why does the universe contain matter at all instead of pure energy? At the same time, atomic research is branching into realms that bridge the gap between physics, chemistry, and biology. Researchers use atomics, scale imaging to observe the inner workings of cells, viruses, and even DNA, revealing life's machinery in unprecedented detail. The same principles that govern atomic particles are now being applied to understand how consciousness might arise from the quantum interactions of neurons. A question that merges science with philosophy. The atom, once a symbol of pure physics, has become a key to unlocking the mysteries of life and thought. Meanwhile, the ethical dimension of atomic science continues to evolve. The discovery of nuclear energy in the mid-20th century revealed both the brilliance and the danger of human intellect. The same processes that can power cities can also destroy them. Today, as the world faces climate change and energy crises, atomic research once again stands at the center of a moral crossroads. Scientists are developing safer nuclear reactors, fusion technologies that mimic the power of the stars, and sustainable systems that could one day provide limitless clean energy. Yet each step forward carries the shadow of responsibility, the reminder that knowledge must be guided by wisdom. The dream of controlled nuclear fusion, long considered impossible, is now within reach. In laboratories around the world, immense machines use magnetic fields to confine plasma hotter than the surface of the sun. If mastered, fusion would transform the human future, offering energy without pollution, danger, or scarcity. It is a vision of hope that embodies the best of atomic science, the belief that understanding the atom can help humanity live in harmony with nature rather than in opposition to it. Beyond practical innovation, the continuing evolution of atomic research challenges the limits of imagination. The boundaries between physics and philosophy blur as scientists contemplate the possibility of multiverses, hidden dimensions, and quantum realities where every possibility exists simultaneously. The same equations that describe atomic interactions may also explain the birth of the cosmos, hinting that the smallest particles and the largest galaxies are woven from the same fabric of existence. As this scientific odyssey unfolds, one truth remains constant. The atom is not merely a physical object, but a symbol of the human spirit, the relentless desire to know, to question, and to understand. Each discovery opens new doors, revealing deeper mysteries behind them. In that endless pursuit lies the beauty of science itself. The revolution of atomic science did not end with Bohr, Rutherford, or Einstein. It continues with every experiment, every question, and every curious mind willing to explore the unknown. Humanity now stands at a moment where the boundaries of knowledge stretch further than ever before. The atom, once seen as the smallest unit of matter, has become a bridge between worlds, between science and philosophy, between matter and energy, between what we know and what we still long to discover. The story of atomic science is, in truth, the story of us, a reflection of our endless curiosity, our triumphs, our errors, and our unyielding hope that somewhere in the heart of the atom lies the key to understanding the universe and ourselves. The evolution continues, as does the timeless journey toward the infinite. In the vast expanse of human curiosity, there exists a single, unbroken thread that binds our understanding of the universe, the the search to know what everything is made of. From the glimmering stars to the stones beneath our feet, from the air we breathe to the thoughts firing in our minds, all of it is matter in motion. But the path to discovering the true nature of matter was not a straight one. It was a journey that began in the haze of philosophy, passed through the clarity of reason, and exploded into the brilliant, unpredictable world of atomic science. In the ancient world, when human observation was the only laboratory instrument, thinkers like Aristotle and Democritus gazed upon the natural world and asked the same fundamental question: what is the world made of? Democritus proposed that everything consisted of tiny, indivisible particles called atoms, a word he took from the Greek atomos, meaning uncuttable. It was a daring leap of imagination, unsupported by experiment, yet profound in its intuition. Aristotle disagreed. To him, the world was a blend of four basic elements: earth, air, fire, and water, interacting through qualities of hot, cold, wet, and dry. For nearly 2,000 years, Aristotle's view dominated thought, shaping how people interpreted the universe. The age of reason and experimentation that followed centuries later would change everything. During the 17th century, the scientific revolution began to loosen the grip of ancient philosophy. Thinkers like Galileo Galilei, Johannes Kepler, and Isaac Newton introduced a new way of understanding nature, not through speculation, but through mathematics and observation. Galileo's telescopes revealed moons orbiting Jupiter, shattering the old, Earth-centered cosmos. Kepler's laws described planetary motion with mathematical precision. And then Newton, with his monumental Principia Mathematica, unified heaven and earth under a single framework of motion and gravity. Classical physics was born. Its language was geometry, its rhythm was cause and effect, and its guiding principle was determinism, the belief that if you know the conditions of a system, you can predict its future with perfect certainty. Newton's universe was a grand machine, governed by precise laws. Every planet, every pendulum, every particle was part of a perfectly ordered mechanism, ticking with eternal regularity. Within this elegant framework, there was no room for randomness or uncertainty. Everything had a place and a reason. The success of classical mechanics was overwhelming. It could describe the motion of cannonballs and comets alike. It could predict eclipses centuries in advance and explain the motion of tides. For generations, it seemed that the dream of total understanding was within reach. If the laws of nature were mechanical and exact, then the universe was knowable, perhaps even controllable. But hidden beneath this perfection was a mystery, a question that classical physics could not answer. What was matter itself? What was the substance that formed the planets, the air, the living beings? Newton had described how matter moved, but not what it was made of. The nature of matter remained an unsolved enigma. In the early 19th century, an English schoolteacher named John Dalton resurrected an ancient idea and gave it a modern mathematical face. He proposed that each element consisted of tiny particles called atoms, and that these atoms combined in fixed ratios to form compounds. Dalton's atomic theory explained why chemical reactions always occurred in definite proportions, why water, for example, always contained the same ratio of hydrogen to oxygen. For the first time, chemistry and physics began to merge into a unified story of matter. Dalton's atoms were solid, indivisible spheres, like miniature billiard balls. They were simple, uniform, and eternal. This model fit neatly into the classical view of nature. It was deterministic, mechanical, and measurable. Scientists could calculate, weigh, and balance atoms as if they were miniature planets. It was a comforting picture, and for a time it seemed complete. Yet, the deeper scientists looked, the more cracks appeared in the smooth surface of classical certainty. By the mid-19th century, new discoveries in electricity, magnetism, and radiation began to reveal behaviors that the old laws could not explain. The universe was no longer as mechanical as Newton had imagined. Forces invisible to the eye, electric fields, magnetic lines, radiant energy, hinted at hidden layers of reality. Michael Faraday, a self-taught experimental genius, uncovered the intimate relationship between electricity and magnetism. His discovery of electromagnetic induction laid the groundwork for the age of electric power. But Faraday's vision was not one of particles colliding like billiard balls. It was a vision of invisible fields spreading through space. To him, forces were not transmitted by contact, but by continuous influence. His ideas were later refined by James Clerk Maxwell, whose equations unified electricity, magnetism, and light into a single theory of electromagnetism. Maxwell's equations were elegant and profound. They predicted that light itself was an electromagnetic wave, ripples in a vast, invisible ocean of fields. Suddenly, the universe seemed alive with energy and motion at every scale. But with this came a new puzzle. Waves, according to classical physics, needed a medium through which to travel: water for ocean waves, air for sound waves. So, what was the medium for light? Scientists called it the luminiferous ether, an invisible substance thought to fill all of space. It was the last remnant of the old metaphysical ideas, a ghostly fabric upon which the universe supposedly floated. Then came the experiment that would change everything. In 1887, Albert Michelson and Edward Morley set out to detect the motion of the Earth through this ether. Their results were shocking. There was no sign of it. Light, it seemed, did not need a medium at all. The experiment defied all expectations and planted the seeds of a revolution that would erupt in the next century. At the same time, new discoveries about the atom itself began to reveal its complexity. In 1897, J. Thomson, experimenting with cathode rays, discovered the electron, a tiny, negatively charged particle, far smaller than any atom. The atom, once thought indivisible, had been split open. It was not the smallest unit of matter after all, but a miniature system of parts. This was the beginning of the end for the classical view of the atom. Thomson imagined the atom as a sphere of positive charge with electrons embedded within it, like raisins in a pudding, a model that explained some properties but raised even more questions. If electrons were inside atoms, what held them there? How were they arranged? And what forces governed their motion? A few years later, Ernest Rutherford performed his famous gold foil experiment. By bombarding thin sheets of gold with alpha particles, he expected them to pass through evenly if the atom was uniform. Instead, a small fraction bounced back as if striking something solid. Rutherford concluded that most of the atom's mass was concentrated in a tiny central nucleus, with electrons orbiting far around it. The atom was mostly empty space. This discovery was both thrilling and unsettling. It shattered the comforting solidity of matter. Everything, tables, rocks, even our bodies, was composed mostly of emptiness. The universe that classical physics had painted as smooth and continuous was suddenly full of voids and invisible forces. And yet, even this new atomic model was still bound by classical ideas. Rutherford imagined electrons orbiting the nucleus much like planets around the sun. But such orbits, according to the laws of electromagnetism, would radiate energy and collapse within fractions of a second. Clearly, something was missing. The equations of Newton and Maxwell could no longer describe the world of the very small. In 1913, a young Danish physicist named Niels Bohr took a daring step beyond classical reasoning. Drawing on the new quantum ideas emerging from Max Planck's work on radiation, Bohr proposed that electrons could occupy only specific, quantized orbits. They could jump between these orbits by absorbing or emitting fixed amounts of energy, quanta. The Bohr model was strange, almost mystical, yet it worked. It explained the spectral lines of hydrogen with astonishing precision. For the first time, the atom could be both mechanical and quantized, both familiar and alien. Bohr's theory marked the beginning of the true transition from classical physics to modern atomic science. It introduced the concept that nature was not continuous but discrete, that energy, matter, and even motion came in packets. The universe, once seen as a clockwork machine, was now more like a symphony of probabilities. The transformation did not stop there. In the decades that followed, a new generation of physicists, Heisenberg, Schrödinger, Dirac, and Einstein, would dismantle the last remnants of classical certainty. They showed that at the atomic level, the world behaved in ways no human intuition could predict. Particles could act like waves. Observation itself could alter outcomes. The deterministic universe of Newton gave way to the probabilistic universe of quantum mechanics. Looking back, this transition was more than a scientific change. It was a shift in world-view. Classical physics had given humanity confidence in the power of reason, the promise that everything could be measured and predicted. Modern atomic theory replaced that certainty with wonder, humility, and a recognition of mystery. The universe was not a machine to be mastered, but a living tapestry of interactions, unfolding according to laws that sometimes defied logic. Yet, this new understanding did not diminish the beauty of science. On the contrary, it revealed a deeper, more intricate order, one that connected the smallest particles to the largest galaxies. Atomic theory showed that the same forces governing the nucleus also shaped the stars. Every atom in our bodies was forged in the heart of an ancient supernova, linking us to the cosmos in a literal, physical way. The transition from classical physics to modern atomic theory is, in many ways, the story of humanity's intellectual awakening. It is a journey from the visible to the invisible, from certainty to curiosity. Each discovery built upon the last, not by erasing old knowledge, but by expanding its boundaries. Newton's laws still hold true for the motions of planets and bridges, but within the atom, new rules apply, rules that challenge our perception of reality itself. As the 19th century turned into the 20th, this revolution transformed not just science, but society. Electricity, radio, and the early study of radiation began to reshape technology and medicine. The new atomic understanding opened the door to inventions that would define the modern world. Yet, behind these achievements lay centuries of human thought, from the musings of Greek philosophers to the equations of modern physicists, all driven by one simple question: what is the universe made of? The answer, as we discovered, was far more beautiful and complex than anyone could have imagined. Matter was not solid but dynamic, not fixed but fluid, built of waves and fields and probabilities. The old boundaries between physics, chemistry, and philosophy blurred into one unified quest for truth. And so, the story of the transition from classical to atomic science is not merely a chronicle of discoveries. It is a story of vision, of minds that dared to see beyond the obvious, to question the familiar, and to imagine the invisible. It reminds us that every era of certainty eventually gives way to new horizons of doubt and discovery. What once seemed final becomes merely the beginning of another chapter. As humanity stepped across the threshold of the 20th century, the classical world faded like an ancient map, replaced by a landscape of subatomic mysteries. Beneath the visible reality of matter, a deeper truth shimmered, a truth woven from quanta, energy, and uncertainty. The journey that began with Aristotle's elements and Dalton's spheres had evolved into the dazzling, unpredictable dance of atomic and quantum worlds. And though the classical age had ended, its legacy endured. It had given us the language of precision, the tools of reason, and the courage to seek patterns in chaos. The revolution of atomic science did not destroy classical physics, it transcended it, showing that truth is not a fixed destination, but a moving horizon. In that realization lies the essence of human progress, our ability to let go of the familiar, to see beyond the limits of our own understanding, and to keep asking endlessly, fearlessly, what lies beneath the surface of things. The world that emerged from the ashes of classical certainty was unlike anything humanity had imagined. The simple, mechanical universe of Newton had dissolved into a realm of mystery and paradox, where the very act of observation could alter reality itself. The transition to modern atomic theory was not only a transformation of science, it was a revolution in the human mind. It forced us to redefine what we meant by truth, by reality, and even by existence. At the beginning of the 20th century, the old boundaries of knowledge began to crumble at an astonishing pace. Scientists were confronted with experimental results that defied every established law. When Max Planck studied the radiation emitted by hot objects, what we now call blackbody radiation, he found that the classical theories predicted absurd results. According to Newtonian and Maxwellian physics, an object heated to a high temperature should emit infinite energy at short wavelengths. Yet this ultraviolet catastrophe never occurred. To resolve the paradox, Planck made a radical assumption. Energy is not continuous, but comes in discrete packets, quanta. This simple idea, introduced in 1900, cracked open the door to quantum theory. Planck himself considered it a mathematical trick, a temporary fix to make the equations work. But the universe would soon prove that his quanta were more than a convenient fiction. They were the true language of nature. Albert Einstein, then a young patent clerk with a restless mind, took Planck's concept and pushed it further. In 1905, he proposed that light itself consists of particles, photons, each carrying a discrete quantum of energy. This explained the photoelectric effect, in which light striking a metal surface could eject electrons only if its frequency was high enough. No matter how bright the light, if its frequency was below a certain threshold, no electrons escaped. This discovery was astonishing. Light, which Maxwell had shown to be a wave, was now also behaving like a particle. The universe was whispering a profound secret. Nature was not one thing or another, but both, depending on how we looked at it. The comfortable clarity of classical physics was gone forever. The universe had revealed its dual nature, wave and particle, continuous and discrete, deterministic and probabilistic. As the scientific community struggled to comprehend this new reality, a second revolution unfolded deep within the heart of the atom. In 1911, Ernest Rutherford's model had shown that atoms consist of a dense nucleus surrounded by orbiting electrons. But this model was unstable under classical physics. Electrons should radiate energy as they orbit and spiral into the nucleus. To explain why atoms were stable, Niels Bohr introduced the idea of quantized energy levels. Electrons could exist only in specific orbits and could move between them only by absorbing or emitting quanta of light. Bohr's theory was elegant, and its predictions matched experimental data perfectly, but it raised unsettling questions. Why should electrons obey such strange, rule-breaking behavior? Why did nature prefer jumps and quanta instead of smooth transitions? Bohr had no answer, but his model marked the first true step into the quantum world. The classical picture of electrons as tiny planets orbiting a miniature sun could no longer hold. Matter, it turned out, was not made of little balls spinning through empty space. It was something far more abstract, a pattern of probabilities, a cloud of potentiality waiting to be observed. By the mid-1920s, two extraordinary minds would translate this mystery into mathematics. Werner Heisenberg, a young German physicist, developed a new framework known as matrix mechanics. Instead of describing the paths of electrons, he focused on their measurable quantities, energy levels, frequencies, intensities. The equations were strange and abstract, yet they matched experiments with breathtaking accuracy. Almost simultaneously, the Austrian physicist Erwin Schrödinger developed wave mechanics, treating electrons not as particles, but as standing waves of probability. His famous wave equation could describe the behavior of electrons in atoms with astonishing precision. It was a triumph of mathematical beauty and physical insight, but it came with a cost. It described possibilities, not certainties. And then came Heisenberg's own shocking realization. It was impossible to know both the position and momentum of a particle with absolute precision. The more accurately one was measured, the less certain the other became. This was not a limitation of our instruments, but a fundamental property of nature itself. Reality, at its most basic level, was uncertain. This uncertainty principle shattered the final remnants of classical determinism. In Newton's universe, every effect had a cause. If one knew the position and velocity of every object, the future was predictable in principle. But in the quantum universe, probability ruled. The atom was no longer a miniature machine, but a realm of chances and possibilities. Albert Einstein, though instrumental in the birth of quantum theory, could never accept its philosophical implications. God does not play dice with the universe, he famously remarked. Yet experiment after experiment confirmed that Heisenberg's uncertainty was not a flaw, but a feature of reality. The universe, it seemed, did play dice, and the rules of that game were written in quantum mechanics. The transition from classical physics to modern atomic theory was more than just the discovery of smaller particles. It was a redefinition of existence. The atom was no longer a simple sphere of matter, but a dynamic structure of energy, probability, and waveforms. Matter and energy became interchangeable, as Einstein's equation E equals mc2 revealed. Space and time themselves were no longer fixed backdrops, but flexible dimensions intertwined in the fabric of relativity. What had begun as an attempt to understand the structure of matter had turned into a revolution in our conception of the universe. The classical idea of separateness, of particles as distinct entities moving in a void, gave way to a new picture of connectedness. Everything was linked through fields and probabilities, through interactions that transcended distance and even time. By the 1930s, this revolution began to manifest in practical and often unsettling ways. The discovery of the neutron by James Chadwick completed the basic picture of the atom's nucleus. With protons, neutrons, and electrons accounted for, scientists now sought to understand the forces binding them. The strong nuclear force, holding the nucleus together against the repulsion of protons, and the weak nuclear force, responsible for radioactive decay, entered the lexicon of physics. The deeper physicists probed, the stranger the universe became. Quantum mechanics, with its equations and uncertainties, could predict the behavior of particles with astonishing accuracy, yet it defied all classical logic. Particles could tunnel through barriers they should not cross. They could interfere with themselves like waves on a pond. Two particles could become entangled, their fates linked instantaneously across vast distances. A phenomenon Einstein derided as spooky action at a distance, but which later experiments proved to be real. In the laboratories of Europe and America, new machines began to emerge, particle accelerators that hurled subatomic particles at near light speeds, smashing atoms apart and revealing the zoo of particles within. The atom, once thought to be the ultimate building block, turned out to be a complex world of its own. Protons and neutrons were themselves made of even smaller entities, quarks, bound together by the exchange of gluons. As modern physics advanced, the line between matter and energy blurred completely. Particles could be created from pure energy and annihilated back into it. The universe seemed to pulse with a hidden rhythm of creation and destruction, of appearance and disappearance. The classical dream of a stable, predictable cosmos had given way to a dynamic, ever-changing reality, a cosmic dance of probabilities. The philosophical implications were immense. The old scientific vision of an objective, observer, independent world crumbled under the weight of quantum discoveries. In the quantum realm, the observer and the observed were intertwined. The act of measurement itself influenced the outcome. Reality was not merely out there, waiting to be discovered. It was, in some sense, created through observation. This raised profound questions that went beyond physics. What did it mean to observe? Was consciousness itself a fundamental part of the universe? Some scientists recoiled from these questions, insisting that physics should concern itself only with predictions, not metaphysics. Others, including Bohr and Heisenberg, embraced the mystery, suggesting that quantum theory represented the limits of human knowledge, that nature was not obligated to conform to human expectations. Through all this upheaval, one truth became clear. Classical physics had not been wrong, only incomplete. It was an approximation, a brilliant, beautiful map that described the macroscopic world with near-perfect accuracy, but failed when applied to the subatomic landscape. Newton's laws still govern planets and pendulums, but they are but a shadow of the deeper laws that operate beneath them. This realization marked a turning point in human thought. For centuries, science had sought absolute truth, a final set of laws to describe everything. But the atomic revolution taught us that truth is layered, contextual, and ever-evolving. The universe reveals itself differently at different scales, each level with its own language and logic. As technology advanced, the fruits of this revolution began to reshape civilization. The understanding of atomic energy led to the development of nuclear power, promising clean, nearly limitless energy, but also unleashing the destructive force of nuclear weapons. In medicine, radioactive isotopes became tools for diagnosis and treatment, saving lives daily. In electronics, the behavior of electrons in semiconductors laid the foundation for computers, smartphones, and the digital age. Every aspect of modern life, from energy to communication, from materials science to cosmology, is built upon the foundations of atomic and quantum theory. The transition from classical to modern physics did not merely change our textbooks. It redefined the very fabric of our existence. Yet, despite all we have learned, the mystery remains. The quantum world continues to challenge intuition. Physicists still debate the true meaning of quantum mechanics, whether the wave function represents reality itself or just our knowledge of it, whether the universe splits into countless branches at every quantum event, or whether hidden variables might someday restore determinism. The more we learn, the more we realize how much we do not yet understand. The transition from classical to atomic science was not the end of discovery, but its beginning. It opened the door to new fields: quantum field theory, particle physics, cosmology, and quantum computing, each revealing deeper layers of reality. Today, as scientists probe the quantum vacuum, manipulate single atoms, and explore the boundaries between matter and energy, they carry forward the legacy of that great transition. The questions that drove Democritus, Newton, Dalton, and Bohr are still alive. Only the tools and the scales have changed. The story of this transition is, ultimately, the story of human curiosity. It is a testament to our willingness to challenge assumptions, to abandon even our most cherished ideas when evidence demands it. It reminds us that knowledge is not a fixed monument, but a living flame, one that must be fed by doubt, wonder, and imagination. Standing on the shoulders of giants, we see further than ever before, but we also see the vastness of what remains unknown. Somewhere beyond the quantum horizon lies another revolution waiting to unfold, perhaps one that will once again redefine our understanding of matter, energy, and reality itself. From the flickering lamps of ancient philosophers to the glowing screens of quantum computers, humanity's quest to understand the atom has been a journey from simplicity to complexity, from certainty to mystery, and from mechanical order to cosmic possibility. The transition from classical physics to modern atomic theory was not just a scientific revolution. It was a revolution of perception, a reawakening of wonder in the face of the unknown. And as we continue to explore, to question, and to dream, the story of that transition lives on, not in the equations alone, but in the unending human desire to understand the universe and our place within it. Long before the atom became a symbol of scientific power, before its image adorned laboratory walls and textbooks, it was a whisper in the minds of philosophers. For thousands of years, humanity believed that the atom was the smallest, most indivisible unit of matter, solid, eternal, and unchangeable. John Dalton's atomic theory in the early 19th century had given this ancient idea a scientific form, describing atoms as tiny, featureless spheres. But as the century unfolded, a quiet storm began to rise within the walls of the atom itself. What appeared to be solid and indivisible was, in truth, a universe within a universe. The discovery of the atom's internal structure was one of the most astonishing scientific revelations in human history. It shattered the illusion of simplicity and opened a gateway to the hidden architecture of reality. To understand how this discovery unfolded is to trace the moment when science looked inward and found infinity. The 19th century was a golden age for experimentation. Laboratories across Europe buzzed with curiosity. Electricity and magnetism, once mysterious curiosities, were being tamed and studied with mathematical precision. Yet these very studies would soon lead scientists to suspect that the atom, long thought indivisible, might not be as simple as it seemed. In 1838, the English scientist Michael Faraday, while experimenting with electrical discharges in gases, observed strange glowing streams inside evacuated glass tubes. These mysterious rays, which later became known as cathode rays, fascinated scientists. They seemed to emerge from the negative electrode, or cathode, and travel in straight lines, casting shadows and making the glass glow when they struck it. Were these rays waves of some kind, or were they streams of particles too small to see? For decades, no one knew. The atom remained, in theory, unbreakable, but the clues were accumulating and the mystery deepened. By the late 1800s, new tools of science, vacuum pumps, electrometers, and fluorescent screens allowed researchers to probe deeper into the nature of these invisible rays. Then came J. Thomson, a modest and methodical physicist at the Cavendish Laboratory in Cambridge. In 1897, Thomson performed a series of groundbreaking experiments using a cathode ray tube. He found that these rays could be deflected by both electric and magnetic fields, and crucially, that the degree of deflection indicated that the rays were composed of particles far smaller and lighter than atoms. He had discovered the electron, the first subatomic particle ever identified. The discovery was nothing short of revolutionary. For the first time, scientists had direct evidence that the atom was not indivisible after all. It had internal parts. Matter was divisible, and inside the atom lay a new world of structure and motion. Thomson's experiments also allowed him to measure the charge-to-mass ratio of the electron, revealing that it was roughly 2,000 times lighter than a hydrogen atom. To describe his discovery, Thomson proposed what became known as the plum pudding model of the atom. In this model, the atom was envisioned as a positively charged sphere, the pudding, with negatively charged electrons embedded within it like plums in a dessert. It was an appealing image, one that kept the atom's overall neutrality intact. For a while, this model satisfied both the imagination and the mathematics of physicists. But nature, as always, had other plans. In 1896, just a year before Thomson's discovery, another phenomenon had shaken the scientific world: radioactivity. Henry Becquerel had found that uranium salts emitted invisible rays that could fog photographic plates, even in darkness. Soon after, Marie and Pierre Curie discovered two new radioactive elements, polonium and radium, and showed that radioactivity was a property of atoms themselves. The atom was not only divisible, it was unstable. Something inside it could transform and emit energy spontaneously. This discovery sent shockwaves through the scientific community. If atoms could decay and release energy, then they must possess an internal mechanism, a hidden source of power that classical physics could not explain. The atom, once the symbol of permanence, had become a dynamic, energetic entity. At the dawn of the 20th century, Ernest Rutherford, a brilliant New Zealand-born physicist, took on the challenge of unraveling this mystery. Building on his work with radioactivity, Rutherford and his students at the University of Manchester conducted a series of experiments that would forever change our understanding of the atomic world. They bombarded thin sheets of gold foil with alpha particles, tiny, positively charged particles emitted by radioactive substances. According to Thomson's plum pudding model, the alpha particles should have passed straight through with minimal deflection. But to Rutherford's astonishment, some of the particles bounced back, as if they had struck something incredibly dense and hard inside the atom. Rutherford described his shock with vivid humor. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. From these results, Rutherford concluded that the atom was mostly empty space, with nearly all its mass concentrated in a tiny, positively charged nucleus at the center. The electrons orbited this nucleus, held in place by electrostatic forces. The nucleus was unimaginably small, If the atom were the size of a stadium, the nucleus would be no bigger than a marble, yet it contained almost all the atom's mass. This discovery was a scientific earthquake. The atom was no longer a solid sphere or a uniform pudding, but a vast, mostly empty structure dominated by an infinitesimal core. The world that had seemed continuous and smooth was, at its foundation, mostly void. The concept of the nucleus also explained radioactivity. Certain atoms had unstable nuclei that could spontaneously break apart, releasing enormous amounts of energy. It was a glimpse into the tremendous forces that bound the atomic world together, forces that, decades later, would be harnessed in both creation and destruction. But Rutherford's model raised new questions. If electrons orbited the nucleus like planets around the Sun, why didn't they radiate energy and spiral inward, as classical physics predicted? According to Maxwell's equations, any accelerating charge should emit electromagnetic radiation. If that were true, atoms would collapse in a fraction of a second. Clearly, something was missing from the classical picture. The solution came from Niels Bohr in 1913, who combined Rutherford's nuclear model with the revolutionary ideas of quantum theory proposed by Max Planck and Albert Einstein. Bohr suggested that electrons could occupy only certain allowed orbits, or energy levels, around the nucleus. When an electron jumped from one orbit to another, it emitted or absorbed a quantum of energy, a photon. Bohr's model explained the spectral lines of hydrogen, which had puzzled scientists for decades. Each line corresponded to a specific energy transition between orbits. This was not just a mathematical trick. It was evidence that atomic structure was quantized, governed by rules that defied classical logic. Through Bohr's insights, the atom was no longer merely a physical object. It was a quantum system, a bridge between the macroscopic world we see and the invisible, probabilistic world beneath. Still, the journey of discovery did not end there. As experimental techniques improved, scientists began probing even deeper into the nucleus itself. Rutherford himself discovered the proton in 1917, demonstrating that the nucleus contained positively charged particles. Later, in 1932, James Chadwick identified the neutron, an electrically neutral particle roughly the same mass as the proton. This solved one of the lingering puzzles: how the nucleus could contain multiple protons, all positively charged, without flying apart due to repulsive forces. The neutrons provided the glue, a new, powerful nuclear force that held the core together. With the proton and neutron established, the architecture of the atom seemed complete. The atom now consisted of a tiny nucleus of protons and neutrons, surrounded by a cloud of electrons. The once indivisible atom had become a complex system, dynamic and layered, a universe of forces and interactions at an unimaginably small scale. Yet, as physicists celebrated their triumph, new mysteries emerged. How exactly did these particles interact? What was the nature of the forces binding them? And what gave them mass in the first place? The search for answers would lead to the birth of quantum mechanics and nuclear physics, fields that redefined the limits of human understanding. But at the dawn of this new age, one truth was already clear. The atom was no longer the end of the journey, it was the beginning. The discovery of the atom's internal structure transformed science at every level. It revealed that matter was not continuous, but made of organized layers of energy and particles. It exposed the staggering power hidden within the tiniest components of the universe. And it showed that the apparent solidity of the world is an illusion, that beneath every object lies an intricate dance of particles and forces, bound by laws of unimaginable precision. In a way, the exploration of the atom mirrored the expansion of human awareness itself. Each time we looked closer, new worlds appeared. The discovery of electrons, protons, and neutrons was not merely the mapping of subatomic geography. It was a revelation about the interconnectedness of all things. The same particles that make up the stars are the ones that form our bodies and the air we breathe. The same forces that hold the nucleus together hold galaxies in their cosmic embrace. By the early 20th century, humanity had pierced the veil of the visible and glimpsed the machinery of creation. The old, simple atom, a symbol of permanence, had given way to a vision of ceaseless energy, transformation, and unity. And yet, in the silence of the laboratory, amid the hum of electric fields and the flicker of phosphorescent screens, the discovery of the atom's inner world carried with it a sense of awe. Scientists were not merely uncovering facts, they were witnessing the hidden poetry of the universe, the rhythm of particles dancing to the music of unseen forces. The revelation that the atom contained structure, that it held within it both chaos and order, power and fragility, marked one of the greatest intellectual leaps in history. It was a moment when human curiosity cracked open the foundation of existence and found that the smallest things were, in truth, the most profound. The atom, once imagined as the smallest and simplest building block of nature, had been unveiled as an intricate universe of its own. But what scientists discovered in the early 20th century was only the beginning. The realization that the atom contained electrons, protons, and neutrons opened a door to an even deeper mystery, the forces and particles that lay within and between them. The quest to understand the atom's internal structure became not just a scientific pursuit, but a journey into the very heart of matter itself, where energy, space, and time intertwined in ways that defied human intuition. After Rutherford and Chadwick revealed the existence of the atomic nucleus and the neutron, the scientific world stood at the edge of a vast new frontier. The nucleus was incredibly dense, tiny beyond comprehension, yet it held nearly all the mass of the atom. What kind of force could hold protons together against their mutual electrical repulsion? What invisible glue prevented this miniature cosmos from flying apart? In the 1930s, scientists began to uncover the answers. The strong nuclear force, a fundamental interaction far more powerful than gravity or electromagnetism, was proposed to explain the cohesion of the nucleus. Though its nature was not yet fully understood, it was clear that this force operated only over incredibly short distances, binding protons and neutrons together with unimaginable strength. It was the secret of atomic stability and also the source of atomic power. At the same time, another mystery unfolded. Radioactivity, first studied by Becquerel and the Curies, revealed that some nuclei were unstable, transforming spontaneously into other elements. This process released vast amounts of energy, suggesting that matter and energy were interchangeable, an idea confirmed by Einstein's equation E equals mc2. The atom, once thought to be a passive particle, was now seen as a dynamic storehouse of energy. Within its tiny nucleus resided the power of the stars. As experiments grew more precise, the structure of the atom was explored with increasingly sophisticated tools. In the 1920s and 1930s, particle accelerators were invented, machines that could hurl charged particles at tremendous speeds and smash them into atomic nuclei. Each collision peeled back another layer of the atomic mystery, revealing new particles and interactions.